Okay, so the first thing we probably ought to recognize is that this is not a one-dimensional problem any more than the last fin that we talked about was a one-dimensional problem. This is a two-dimensional problem, right? If I am a piece of energy and I start here at the base, how do I get out? I have to move in the radial direction, but I also have to move in the x direction, either up or down, in order to get to this surface before I'm convected, right? So if I were to look at the temperature distribution inside of this fin, I should see that there's temperature gradients in the r direction, but also in the x direction. And it sure would make my life a lot easier if I could ignore the temperature gradients in the x direction as being small, so that this was only a problem where temperature was a function of r. And so in order to justify that, I would need to calculate a BO number. And the BO number ought to be the ratio of the resistance that I'd like to throw away, and the resistance that I'd like to throw away is the resistance to conduction in the x direction, and I would divide that by the resistance from the surface to the surroundings, which is R convection, right? So I've calculated that BO number here, approximately anyway. So let's look at this. This is the resistance to conduction in the x direction. So that's going to be how far do I have to move energy to get it from the center to the surface. That's the thickness over 2 times K times what's the area that I have for conduction if I'm moving energy in this direction. And that would be pi times R out squared minus R in squared. So this is one resistance, right? And of course, resistances are never small relative to themselves. I have to compare that to the resistance associated with getting the energy from the surface to the surroundings, and that is 1 over h bar times this area, so pi times r out squared minus r in squared, and of course the pi's cancel and the r outs minus r in squareds cancel, and this is my BO number. So I would look at that BO number and calculate it. Hopefully it's a lot less than 1, and we're going to assume that it is. If it's a lot less than 1, then we can go ahead and make the extended surface approximation and solve the problem that way, right? So we'll go through and quickly derive the differential equation. I'm hoping at this point that you've done this enough times that it's relatively easy. So I have a differential control volume. If I can make the extended surface approximation, my differential control volume extends differentially in the r direction, but it extends all the way across the fin in the thickness, and then actually all the way 360 degrees around the fin in the circumferential direction, because there's no temperature gradients in the x direction, and there's definitely no temperature gradients in the theta direction. So there's my control volume. My energy balance says in is q dot r at location r, out is q dot in the radial direction at location r plus dr, and then I've defined convection as being out as well. So there's my energy balance. I'll do the usual thing. I take this q dot at r plus dr and expand it and take the limit as dr goes to 0. And when I make that substitution, this is what I get, right? I need some rate equations. So this first term here is a conduction term. So that's going to be minus k times the area. So the area for conduction is the area right here, 2 pi r times the thickness times dt dr. So that's what I'll put there. And then q dot convection is, well, it's the total surface area exposed to fluid inside of this control volume. So the top would be 2 pi r times dr, and the bottom would be another 2 pi r times dr. So I get 4 pi r times dr, and then h bar times t minus t infinity, because I've defined this as being out. So I substitute these two guys into here. I'm going to divide through by everything in the highest order derivative that's constant. So minus k 2 pi, not r, that's definitely not a constant, and the thickness, and I'll divide through by that, and this is what I get. I'm really not sure why I have this twice, given it's the same equation, but this is again what I get, so reinforced that I get, I guess. And then the last thing I'm going to do is just take this group right here and call it m squared. And I do that for two reasons. One is because I don't really want to write this group over and over again, and two, because I want to make it obvious that this is a positive group, right? So 2 is obviously positive, H bar has to be positive, K has to be positive, the thickness has to be positive. So this is a positive group, right? So there's my differential equation that I get after a little bit of work. And again, hopefully those steps are not very difficult for you at this point. We got to solve this equation. We solve it in the typical way. This is not a separable equation for reasons we talked about last time. Right? We can't put one part on one side and the other part on the other side and integrate both sides separately. It just doesn't work. So instead we have to break this up into a homogeneous and a particular solution. So I make this substitution into here, and I get this equation here. And I have to remember that the homogeneous solution solves a homogeneous differential equation, so this has to be equal to 0, right? And then whatever's left is my particular differential equation, right? So this is what it is, and my only goal with the particular differential equation is to just find a solution. And if I look at this, a solution that's going to work is if the TP is a constant, right? If I put TP equal to a constant here, then I get this term equals this term. The derivative of a constant is 0, so the constant needs to be t infinity. So my particular solution for this problem is just t infinity. It won't always be that easy, but it's certainly that easy for this one. That leaves me only with the task now of solving the homogeneous differential equation. And this might be a differential equation that you haven't encountered before, right? This is not something that's solved by exponentials or sinh and cosh or sine and cosine. This is still a differential equation that pops up often enough that people have found solutions for it. And the solution to this equation is going to be a Bessel function, right? And actually, this is kind of a pretty cool thing to talk about. This equation is a form of a larger class of equations, which we call Bessel's equation. So here's Bessel's equation. This is a differential equation for a function theta in terms of x. And in this equation, p and c and s can be anything, right? And this is still a form of Bessel's equation. So certainly what I have here is a form of Bessel's equation. It's a very specific one. If I look at it, p is 1. C is apparently m, and S must be equal to 1, right? So, but still a form of Bessel's equation. And there's a very logical set of steps that you go through to find the solution to Bessel's equation, right? So as soon as I recognize that this is a form of Bessel's equation, I just have to sort of turn the crank in order to find the solution, right? And here's the flow chart that you go through to find a solution to Bessel's equation. So here's my governing differential equation. This is Bessel's equation. I have to basically follow this flow chart. So the first step in the flow chart is I decide, is s minus p plus 2 equal to 0 or not, right? If it's equal to 0, then I follow this path. There's some other things I have to calculate. If it's not equal to 0, then I follow this path. Most of the time it's not equal to 0, so most of the time you're over here and you calculate some solution parameters, and depending on whether the last term is negative or positive, you get modified Bessel functions or Bessel functions, right? And Bessel functions, like exponential or cosh and sinh or sine and cosine, those are really just names that we've given to polynomial series where the coefficients in the series have been selected to solve a certain differential equation, right? So rather than write out the series, which would be tedious, we give that series a name, we call it sinh, and now we can just use sinh as shorthand for that series, right? But that's the solution to this equation, so it's really useful. So that's all that Bessel functions are, right? So if I want to use these Bessel functions to solve this problem, at this point it's really kind of just pattern matching, right? So here's my equation, here's Bessel's equation. I just got to know which of these parameters in Bessel's equation corresponds to which of these parameters in my equation. So apparently in Bessel's equation, there's an x as the independent variable, so my independent variables are, they use theta, I use t sub h, that's easy. Here x is to the p power, r is to the 1 power, so for me p is equal to 1. Here I have c squared, here I have m squared, so c is equal to m. and then here x is to the s power, r is to the 1 power, so s is equal to 1, right? So these are the substitutions that I need to go through this path. The first thing I need to do is calculate s minus p plus 2. So s minus p plus 2 is 1 minus 1 plus 2, which is 2, and 2 is not equal to 0. So I'm going down this road. The next thing I do is calculate these solution parameters n and a, and then n over a. So n is, let's see, 1 minus p divided by s minus p plus 2. So 1 minus 1 divided by 1 minus 1 plus 2, this is 0. So n is 0. A is 2 divided by s minus p plus 2. So 2, and then 1 minus 1 plus 2. So this is 1. A is 1. And then n over a is 0 over 1 is 0, right? So armed with this, then, I choose my my last path based on whether the last term is negative or positive, right? So if I look at my equation, the last term is clearly negative, right? That was kind of the point of making sure that this is an m squared. Minus m squared is going to be negative. So I'm down here. There's my solution right here, right? So where did I put this? Oh, sorry. Here's my solution right here, right? And all I got to do then is make the substitutions back into this solution to get my solution. So let's see. TH is C1 times X. Well, for us, X is R to the N over A power to the 0 power. Then I have Bessel I, N. So N is 0. C is M. A is 1. And then R to the 1 over A, so the 1 over 1. And the same thing here, right? So here's my solution. R to the 0 is just 1. R to the 1 is just R. Here's my solution. And I guess it is worth talking a little bit about what you call these things. So Bessel I is the modified Bessel function of the first kind, and Bessel K is the modified Bessel function of the second kind, right? And then you'll see there's actually two arguments. The first argument is what's called the order of the Bessel function. So this is the 0th order modified Bessel function of the first kind. And then this is just the argument at which it's being evaluated. This is the 0th order modified Bessel function of the second kind. And again, this is just the argument at which it's being evaluated. So sometimes in books, you'll see this called I0 and K0. If this were the first order, you could maybe see it called I1 and K1. But that's all they are. And any software will have these programmed into it, Ease or MATLAB or Maple or whatever. If my last term would have been negative, I would have been down here, and I would have had Bessel J and Bessel Y, right? So here I had Bessel I and Bessel K. These were modified Bessel functions of the first and second kind. Bessel J and Bessel Y are just Bessel functions of the first and second kind. They behave very differently. These guys tend to decay. These guys tend to oscillate. Well, these behave more like exponentials, I guess I should say. One decays and one rises. And these oscillate like kind of sine and cosine does. Anyway, I have my homogeneous solution. I have my particular solution. I'm kind of done, right? I guess the last thing I would just like to mention is that, the rules for using Bessel functions have been worked out, obviously. If you want to take derivatives or integrate them, there's just formulas that you look up. And Maple is super good at this as well. But here's some useful rules for taking the derivative of Bessel functions should you need to do that, which we will here in a little bit. So here's my solution. This was the differential equation I was trying to solve. I said it was going to be the sum of a homogeneous solution, which I figured out is this, and a particular solution, which I figured out is this. So here's my general solution, right? At this point, I should be back on pretty firm footing, right? I had a differential equation, and I solved it and ended up with a solution that has two undetermined constants, right? This solution to my differential equation will solve this differential equation no matter what I put in for C1 and C2, right? It doesn't matter what I put in there. I got to pick C1 and C2 so that I get the right boundary conditions, right? And that's what we'll do next.